Good morning, everyone. Today I will be presenting an analysis and comparison of different methods for subgraph isomorphism detection in dynamic graphs, with a special focus on Oberoi solution and its performance compared to existing algorithms. Let's start with the problem description. The problem we're addressing is subgraph isomorphism in dynamic graphs. This involves finding instances of smaller pattern graphs within a larger time evolving target graph while maintaining the temporal order of interactions. Existing approaches often aggregate graphs with timestamped edges, which obscure the temporal evolution crucial for certain analysis. This leads to limitations in scenarios where preserving the temporal sequence is vital for understanding interactions over time. Now let us look at how Obroy's model is different. Obroy and the team have introduced an innovative snapshot-based model for subgraph isomorphism. Unlike traditional aggregated models that merge data and lose the order of interactions, this method represents a dynamic graph as a sequence of static snapshots. Their algorithm, an enhancement of the VF3 algorithm used for static graphs, includes an advanced pruning strategies that reduces computational complexity by using previously matched nodes as starting points. Now over to Ryan.
Now, to demonstrate the effectiveness of the snapshot-based solution, Oberoi real-world datasets like email EU core, temporal, and college MSG. The results showed that Oberoi's algorithm outperformed Mackey's, especially for large datasets where memory constraints became an issue. While temporal RI performed faster on very large datasets, Oberoi's method excelled in smaller, temporally sensitive cases. The comparison metrics included execution time, resilience to noise, and accuracy in matching dynamic patterns. Now we will execute the code. Understand the code. The inputs to this code are two dynamic graphs H and G. H is the pattern graph and G is the target graph. The first line represents the number of nodes in the graph, and the next n lines represent informations of the node. Each node has a node ID, out degree, and information about the edges. Discussing the output is a list of subgraphs that match the pattern graph with the target graph at a particular snapshot. For example, at timestamp 0, we have nodes V1 and V100 matching through edges R34 and R35. In subsequent lines of the output, this can be observed for different timestamps. Over to Aves.
So now let's analyze some of the figures. So first we have figure number 3. Figure 3 shows the aggregated graphlet profile for both teams during the match. This profile highlights their strategic tendencies by summarizing subgraphs patterns across positions. Practical constraints like timing gaps restrict certain state transitions. The maximum entropy at 3.322 represents equal state probability and maximum diversity. Now moving over to figure number 4. Figure number 4 compares transition profiles for Argentina, which is present on the left, and Spain on the right. Argentina shows structured patterns with fewer high probability transitions, indicating predictability. Spain displays broader adaptive transitions. The restricted profile shows timing limited transitions. Maximum entropies are 2.658 and 2.356, reflecting maximum unpredictability with equal probability.
Thank you.